Hello, gang. What do we got here? 25 participants, including myself. Just waiting a little bit to see if more people show up. Today we're just going to have a review. Big old exam coming on Friday. Or, no, I'm sorry, Wednesday. COVID time. Who knows what day it is? One day runs into the next. Okay, so I'd like to open the floor at this point, whatever the hell that means, to questions from the crowd. So I'm looking for, if this is a review session, if anybody has any questions, this would be the time to ask them. I'm going to ask questions of you eventually.
Dr. Slish, it's about like how to take the exam. I saw it's like 15 minutes for the multiple choice question and the 60 minutes for the essay question. Like, are they gonna be like continuous, or we can take a break in between? Or
yeah, you can't take a break. Once you open the exam, you've got that amount of time. You can come out of it and go somewhere else. It's going to be open book. You know, there's no way I can stop that. So you can come out of it and go back, but the clock keeps running.
okay.
And the test is for an hour and 15 minutes.
Yeah.
You can do either one first. It doesn't matter. Or, you know, I would suggest doing the multiple choice first, just grinding through them. But you can do the essay first. Just, you know, your essay will close, and then you'll have to do the multiple choice right after it.
Thank you.
Sure. Any other questions or comments? Questions about the material? Oh, can we ask questions about the last quiz? Absolutely, Sean. Wait, Winter Sprutchen, is the exam at a certain time? Yes, the exam is at our normal class time. It'll open up then and it'll close when our class normally ends. So it's right at that time. So going back to Sean Reeser, go ahead and ask your question. Why do receptors upregulate instead of downregulate when you're supposed to antagonist? So, okay, good question. So the basic idea with downregulation is if you overstimulate the receptor, the cell removes them from the membrane to protect itself from overstimulation. Now, the opposite what happens with an antagonist, because you've got receptors out there and they're blocked by the antagonist. So now the cell is getting understimulated. So it puts more receptors out to the surface to try and get stimulation again, basically. It's all about homeostasis. It wants to have a steady state of stimulation. So if it's overstimulated, it pulls the receptors away. Understimulated, it puts more up there. Okay, can you explain the first pass effect a bit more? So everything you eat goes into your stomach. A little bit of absorption there, but not much. Most of your absorption is going to happen in your small intestine. So when food and stuff goes to your small intestine, it gets absorbed into your bloodstream, but it doesn't go into your main bloodstream yet. It goes into this hepatic portal vein. So everything from your intestine all the way down to a third of the rectum, right? All the blood from that goes to your liver first. Basic idea being your liver gets first shot at whatever you eat to detoxify it. So everything you eat will go to your liver first, and then your liver enzymes will break down or metabolize any organic chemical that isn't like normal in your body, like fats and sugars and stuff. It will, you know, do whatever it does with fats and sugars and stuff. But you know, unknown organic chemicals will be acted on by that cytochrome P450 system. Is that good? First pass, Alexis? Can you talk about the difference between inotropic versus metabotropic? Okay, so inotropic are the simplest. They're basically neurotransmitter opened channels. So the channel sits there. When the neurotransmitter comes across a synapse and binds to it, it opens and ions go through. And so that's the simplest thing. Those inotropic channels are either sodium channels, which are exciting, and so they're excitatory postsynaptic potentials. They depolarize and lead the cell closer to an action potential. Or it could be chloride going in, and that's the opposite. So it's hyperpolarizing. It's inhibiting action potentials. So that's called an IPSP. So make sure you know the difference between IPSP and EPSP when we get to the exam, because EPSPs are sodium channels and they're excitatory, depolarizing. IPSPs are chloride and they're inhibitory and hyperpolarizing. Metabotropic now, and in terms of the inotropic, something like 90% of all the activity in your brain are these channels, these inotropic channels. They're very fast because all it is a neurotransmitter comes out, has an effect, neurotransmitter goes away, very fast response. Now the metabotropic are more complicated. The neurotransmitter binds to the receptor activates a G protein, and then the G protein activates something. And how far down the line it has to go to get a response, and the response is always an ion channel. How far it has to go to an ion channel slows down the response. So you could have a metabotropic receptor activate a G protein, and the G protein open a channel. Okay, that's a lot slower than an inotropic channel because you've got 1, 2, 3 different things going on before you get a response. That G protein could activate adenyl cyclic AMP, then opening a channel. That takes a little longer. Or the G protein activates adenyl, which then activates protein kinase A, which then phosphorylates protein. So more and more steps takes longer and longer to happen. But it also will last longer. So metabotropic receptors take longer to produce their effect. There's more steps before you hit the ion channel. And also the effect will last longer. Usually our metabotropic receptors are linked to, could be linked to calcium, but usually they're linked to potassium going out, and that being an IPSP as well. That's rather long-winded. Does that make sense, Celine? There are these primates. I think they're gibbons or baboons or something. When they're angry, they do eye flashes. And these Eastern European browse are really good at it. Okay. How is inhalation from the lungs directly to the brain while IV has to go through more of the circulatory system before it reaches the brain? Uh-oh, was that it? How is inhalation faster route to the brain than? So think about the anatomy, okay? You inhale something into your lungs. From your lungs, it goes to the left side of your heart. From the left side of your heart, it goes out to your body and up to your brain. If you inject something in the arm, it comes into your heart and the right side, then goes out to your lungs, then comes back to your heart, to the left side, and then goes up to your brain. So it's a longer path for something that's injected into the veins than for something that is in your lungs. And Sean is correct. Can you go over graded potentials? Okay, so 2 big different potential. One is the action potential, the other is the graded potential. So I'll talk about both of them. The action potential is all voltage gated channels. So and it only happens in the axon. So the axon depolarizes a little bit, your voltage dependent sodium channels open, boom, the membrane potential shoots way positive, potassium channels open, shoots way negative, and then relaxes, okay? So every action potential does that exact same thing. As long as you get enough stimulation to start it, it goes a full thing. The graded potential is the opposite. It's like and it's not controlled by voltage, it's controlled by neurotransmitter. So your action potentials are controlled by voltage, neurotransmitters on the graded side. So the graded side is when neurotransmitter comes out and it hits a channel, whether it's inotropic or metabotropic, and some ions go through, and then the neurotransmitter goes away. So it's small and it's brief, and it doesn't like totally go to some high positive number. It's just small up and down, up and down, up and down. So action potentials are all or nothing. Graded are, variable. They can be anything. And the more neurotransmitter gets released, the more EPSPs you get, and the more effect you have with it. So action potentials all or nothing. Graded potentials are graded, for lack of a better word. What else do I want to say about that? So again, your graded potentials are your inotropic receptors and your metabotropic receptors. Those are producing graded potentials. Is that good, Julia? Okay. Saltatory conduction. So saltatory conduction, let's start back at the figure before saltatory conduction, which is basically how does an action potential go down the axon? So if you've got an axon and the action potential is here, you've got depolarization here that spreads passively across the membrane and activates channels further down the line. So that action potential, that voltage decreases as you get further away from the site because you've got potassium leaks going out all along the way, and that's decreasing the depolarization. So under normal conditions, you would figure depolarization here, it's going to stretch out, but it's going to decrease exponentially as you get further away from that site because of that potassium leak. Now, saltatory conduction is what happens in your myelinated neurons because you've got like action potential here, and then you've got all this insulation, so there's no potassium leak. And then over here, you've got another node. So that action potential, when it depolarizes here, that depolarization spreads without decreasing all the way down to the next node and activates that node. So it allows that action potential to go a lot faster because the potential is not decreasing as you get further away from the site of the depolarization. Esha, does that make sense? Does that make sense? Yes, okay. Could you explain the difference between ion-gated and ligand-gated channels? Yes. Ion-gated, I think there isn't such a thing as ion-gated. It's voltage-gated, okay? So voltage-gated channels, the only ones we talked about were the voltage-dependent sodium channel and voltage-dependent potassium channel. They are only in the axon, and they're involved in the action potential. So if you look at your axon hillock, when depolarization comes there, it starts to open some of these sodium channels there, voltage-dependent sodium channels. So the voltage is causing the open. That starts an action potential, which then propagates itself all the way down. That's your voltage-gated channel, only in the axon and giving you action potentials. The ligand channels, ligand-gated channels are only for graded potentials and only in synapses. And those synapses are on the soma and then the dendrites. So that's another important thing to keep in mind. Your ligand-gated channels are activated by the ligands, so that only happens in a synapse. Voltage-gated channels are only in the axon. Is that okay, Matt? Okay. Go in depth about liganded channels. Oh, so did I go enough depth or no? Yes or no? I did. Okay. Serena. Okay. First pass effect again. Let me pull up a I'm going to pull up a figure because I've been talking with my hands and it may make more sense if we have figures. Sorry guys, I'm just cleaning up my headspace here. Okay. I don't know if this is the best figure, but this is the figure from your book. So basically, here's your pulmonary circuit, and then here's your systemic circuit over here. So with first pass effect says everything you eat goes into your intestines. So any absorption that happens in the intestines goes through this hepatic portal vein to your liver. So everything absorbed goes to the liver first. So the first time it goes through your circulatory system, first pass, the liver will break things down. So if you've got a drug that's very actively metabolized, like cocaine, swallow it, goes to your liver, and most of it gets broken down really quickly. That's why people don't take cocaine pills. It just doesn't work that well. It's a wasted drug. So that's your first pass effect. Let me see if I can find a better figure. God. What the hell is this? Hang on, I got to take this. Hello? Yes, I am. Let me call you back. I'm in class right now. Let me call you back in about an hour. Okay, bye. Sorry about that. I'm taking care of my dad, and he can't answer the phone, so I gotta check on it. Okay, so, but that is not your problem, is it? No, it's not. Oops. First pass effect. Images. Oops. Hang on a second. All right, let's do this. So here's my first pass effect thing. You take a drug or any food or anything, goes into your stomach to the lumen of the GI tract, and from there it gets taken up, goes to the liver before it goes into the rest of your system. Okay. Dr. Rue, is that okay? Are we good on that? Oops. Oh, shoot. Okay. Okay. Okay, any other questions, comments? My face is all washed out. My computer camera's not working so good. Does the exam focus on one unit more than another? No, I try and spread the questions out over all 3 chapters. So it should be pretty evenly spread out. You may find it differently, but that's what I think. We need to go into detail about how drugs disrupt transmission, or just know the list. You may be asked a question like, here's a synapse and it's overexpressing or whatever. What do you think is happening here? What do you think the drug is doing? You know, so just know the basic mechanisms and realize, like that one exercise we did last week, that any protein in that synapse could be interacted with by a drug and activated or turned off. So in general, you may be asked a question like that. I won't ask to list the 10 different ways a drug can act. I'm more likely to ask, you know, there's this drug, produces effect. What do you think it does? Well, it's going to bind to one of those proteins and inhibit it or activate it. So that's the way that would be asked. Okay, Alexis, do we need to know the structure of the kidneys? No, not at all. Just know the basic function of it and the basic idea. The main thing is polar versus nonpolar. So the basic idea is in the kidney, everything gets dumped out into the collecting ducts, and then polar things that are useful are reabsorbed. Polar things that are not stay in the urine and get released. And the problem with nonpolar things is they can pass membranes. So when they get dumped out into collecting duct, they just passively reabsorb themselves. So that's the only point to that kidney thing, that in order for the kidney to get rid of something, it has to be made more polar. And it's made more polar in which organ? Chat it. First person gets a bonus. First person gets
Liver.
10. Liver. Who said liver?
Alexis.
Okay, you get $10. Submit your invoice to the registrar. They will refund you $10 for that.
All right, I'll get right on it.
Any other questions? If not, oh, good. What are some ways to stop neurotransmitters? Well, how do you stop a neurotransmitter? One way would be at the postsynaptic side, block the receptor. Another way would be to block the vesicle from fusing. Botulinum toxin does that. Another way would be to activate the presynaptic autoreceptor. You could, there are some drugs that will displace the neurotransmitter from the vesicle. So basically something that looks like the drug gets pumped in there, and something that looks like the neurotransmitter gets pumped into the vesicle, but isn't a neurotransmitter, just fills the vesicle up, and then you got little neurotransmitter in there. There are drugs that do that. You could block the pump that puts neurotransmitters and precursors into those vesicles. That would block it. I guess that's the main ways. Is that a mimic? Okay, Matt, I'm not sure what you're talking about. Can you make that more clear? Is that a mimic? Matt Cole?
Yeah, so we learned in biology about certain drugs and being able to enter to like bond to the receptor. So when you said like a drug that looks similar, but a drug that looks similar to block the vesicle. So I'm like picturing like a drug mimic, but I'm not sure if that is then.
I see what you're saying. Yeah. Yeah. So the drug binding to that postsynaptic receptor could either mimic the neurotransmitter, in which case it would be an agonist. So it's going to activate the receptor.
Okay.
Or it could be an antagonist, and it just binds to it without activating it, and that blocks it. So it was the second one that I was talking about there. Okay, so I got a private question here. I'm going to read it without saying who posted it because I think it's a good question. I don't want to talk about it. What's the concept of that the more drugs you take, the less effect they have? Okay, so this has to do with receptor regulation, which we talked about, I believe, in the last class. Basically, that if you overstimulate receptors, the cell will withdraw them from the membrane. And then because you got fewer receptors, the drug will have less effect. On the other hand, I think this was asked earlier, if your drug is an antagonist and blocks those receptors, then the cell will put more receptors out into the surface, and then you'll get effect again because your drug has less of an effect because there's more receptors. You need more drug to block all those receptors. What else? Does that make sense? So the more you take a drug, if you chronically take a drug at high dose, your receptors downregulate and the drug has less and less effect over time. Okay, 355. Any other questions? What is the difference between axosomatic and axoexonic? Okay, this is chapter 2. So axo is where the presynaptic side of both of these, and then the other half of the word is the postsynaptic side. So you've got axosomatic, which is the axon from one neuron is synapsing with the body of another neuron. Axodendritic, where the axon is binding with the dendrite, and then axoexonic is the most interesting kind, in my opinion, where you've got one axon and it's synapsing with another axon. And so this axon can affect the amount of release from the second axon. And we'll see that a lot in the opiate chapter, which is in a couple of weeks. That's how opiates work. Does that make sense? So axoexonic is just when one axon is synapsing with another axon. And axosomatic is when one axon is synapsing with the soma. the cell body. Drum roll, please. Nothing? Okay. I'm going to leave it open. Leave the chat open. I would like to go over some questions now. The ones from the book or the Moodle page, they're the same. Share my screen. Share my screen. Stop that. Stop that. I'm getting there. Okay. We're there. So those. Yes. Okay. Oops. Damn it. For $10, someone answer this question. Let's see. Describe the route a drug takes to the brain when injected intramuscularly. For $100. What the hell? I'm not paying anyway. Someone want to chat that? Oh, we've got chat.
Muscular.
So integration. Oh.
Isn't it intramuscular?
Yes. If the drug is injected intramuscularly, how does it get to your brain?
Oh. It's absorbed in the capillaries to the vein, to the heart, pulmonary circulation, systemic circulation, and then to the brain, heart and brain.
Exactly. That's all. That's one of my easier questions. That's just to get you some free points, so I don't have to give you bonus points.
3 points. So subcutaneous is just like into your fatty tissue?
Subcutaneous is doesn't have to be fatty tissue, but it's under the skin. You know, you can take a low fat part like your hand, pick it up and inject subcutaneous there, or you can inject it into the fat. I think injecting in the fat would probably be slower than just under the skin because it'd have to get out of that fat area first.
Gotcha.
That's an interesting question. I've never heard of adipose injections. That's an interesting idea. I wonder if anybody
Isn't
does
that like kind of like a Brazilian butt lift? They kind of take like fat and then they inject it into a different spot. I guess they inject it subcutaneously after they take it out of the fat.
Exactly. Yeah.
Because then they put it under the skin to make it fat, right?
Yeah. I wonder if it stays there if the body rejects it. Even if it's coming from your same body, it's not like it's supposed to be there. Does it last?
It's probably like either or. Like it's either going to reject it fully or it's going to be like fine.
Oh, okay. Could I have some put on the top of my head so I can get like a nice little ball up there?
You definitely should. A lump. Just a lump on your head.
A lump head.
That would look great on you. You get a little top hat to cover it sometimes.
Or a wig with the big bun on over the bump. Explain the role of kidney in clearance and why it relies on the liver to perform this role. We kind of talked about this already. Someone want to chat that one? Explain the role of the kidney in drug clearance. What is drug clearance? Oh, here we go.
The first pass effect with the livers and the kidney. So.
Okay.
So it metabolizes like everything that goes through it, pretty much.
Okay, that's first pass effect, but here we're just talking about drug clearance. So now the drug is already in your bloodstream.
Ooh.
Didn't you say that if it's polar or non-polar, it's how it'd be?
Right.
That's the first pass too, isn't it?
That's not first pass anymore. Once it gets past your liver into your bloodstream, then it's no longer first pass. It's just on that first absorption. Although all your blood's going to go through your liver again and get metabolized some more. But first pass is just that first time it gets absorbed and goes through your liver.
Gotcha.
So the role of the kidney in drug clearance. What is the guy who just talked? I didn't know your name. What did you say? Because I think you were there.
Yusuf.
Yusuf. Okay.
Yeah, I was just saying. It depends if the drug is polar or non-polar, like
Right.
you were saying earlier.
But what about polar drugs?
Polar drugs will either. Didn't you say that they would get used in urea?
Right. So,
Yeah.
so when the question says explain the role of the drug kidney in drug clearance, it's getting rid of polar toxins, basically. Okay, that's the role of the liver. And why does it rely? That's the role of the kidneys. Why does it rely on the liver? And Sean Reeser's got it here. Filter out of the blood by the liver, metabolized by the liver, and then sent to the kidneys to be excreted. And Stefan McCain's correct about the polar drugs. Remember, we talked about vitamin C. Take a big dose of vitamin C, it'll be in your urine in a half an hour. Okay, good. Oh, this is one that gets everyone. Not everyone, but most people. Some potent opiates, which activate the same receptors as morphine and heroin, are available as over-the-counter medicines that anyone can buy in the drugstore as anti-diarrheal medicines. This is true. However, they produce no euphoria or sedation like morphine does. Why might this be? It's a pharmacokinetic problem. So you've got this opiate that you can buy in the drugstore. Take the pills and you don't get any central effects, but it does block your intestines and stops your. It's not first pass effect, no, because if it was, a lot of people say first pass effect, but if it was, and an addict wanted to get high, they just crush it up and dissolve it and inject it. I thought it might be because of the blood-brain barrier. Well, Julia, God damn it, you should be 100% sure. That's the answer. So it doesn't have to do with potency either, because you would just take more. You just take more of the drug if you wanted to get more. But yeah, the blood-brain barrier, because these are polar opiate drugs. So they bind to the opiate receptors in your intestines, which decrease intestinal motility and stop your diarrhea. Okay. Julia Waterus gets $100. Just let the registrar know I told you you could have that. I'm sure or the bursars, tell the bursar, they care more. Okay, another pharmacokinetic question. Two people take the same dose of heroin. One snorts it, the other swallows it. One person overdoses and is sent to the hospital. The other is alert enough to call the ambulance. Which one is sent to the hospital and why? This is worth 10 cents. Everybody gets this one right.
One who swallows it is fine.
Right.
Because it's taking a lot longer to reach the brain.
Right. And what else?
Started it, so it went in through inhalation, like you explained to me, and it went straight to his brain through the nose.
Right. So, well, intranasal isn't inhalation. It's like mucous membranes. It gets absorbed directly. So the dose is a lot higher. So when you swallow it, it's going to be slower, which gives you a lower peak, and also first pass effect. So you get less. So the person who snorted it goes to the hospital, and it gets filtered out if orally ingested. Okay.
But I guess you also said that it's possible to overdose when you just swallow it because it really affects late. So you feel like you need more, so like you take more. Is that also true?
That's a possibility too, yeah. It's more so, I don't think opiates are as bad for this as something like MDMA, ecstasy. People tend to double dose on that. A lot of it because they don't really know if they actually got MDMA when they're buying it on the street. And it takes like an hour and a half to kick in. So you're like, that must have been something stupid. So then they'll take something else, take another one, I mean. But also it could happen with heroin too, with opiates too, if you're swallowing them. Okay, that's usually an easier question. Most people get that one right. Okay, these are all pharmacokinetics. This is from chapter 1. Explain why a drug can be detected in the urine for days or weeks after the effect of the drug has worn off. Drugs clear from the body Oh, asymptotically. That's true. That's true. And why, just staying with that one, why would it, why could you detect it after the effect is no longer there? So asymptotically means it peaks, drugs clear from the body. Action potential threshold, no, it doesn't have to do with the action potential. The drug peaks and it comes down and asymptotically approaches zero. And you need a high dose to feel the effect, but you can detect it at a really, really low level. So even though you haven't had it for a few days, they can still detect it at that low level. That's one reason. What's the other reason?
Isn't it just because like your kidneys hasn't and liver haven't filtered it out yet?
Yeah, and why might that be? Like I said, vitamin C would be filtered out in a half an hour. Why would other
It's more like lipid soluble, water soluble.
right? Tanner Tobias, stored in fat. So if it's lipid soluble, it'll be stored in the fat, and it will only slowly come out to the rest of your body. Some are water soluble, others are lipid. Okay, so a lot of people got that. Good. Okay, let's move on to chapter 2 questions. Oops, this guy. Okie doke. Question 1. How are the concentrations of sodium and potassium different inside and outside the cell? How is this used to produce an action potential? Let's just answer the first question. How is the concentration different inside and outside? In other words, which is high inside and which is high outside? I'm waiting.
Sodium is higher outside and potassium is higher inside.
Right, exactly. And what does that have to do with the action potential? How does that affect it?
Isn't it when like the sodium moves in, it creates a depolarization which goes down the axon hillock to either create an action potential or not.
Right. And then what happens with the potassium?
I think it repolarizes.
Exactly.
Yeah.
The idea is sodium's high outside, and when it comes in, the inside depolarizes, becomes positive. That opens the potassium channels. Potassium goes out, repolarizes, makes the inside more negative again. Okay. What is an EPSP? What is an IPSP? How do neurotransmitters produce these in the postsynaptic membrane? EPSP.
Excitatory presynaptic. I don't know what the SP is.
Potential.
Postsynaptic potential.
Yeah. And IPSP is inhibitory.
Inhibitory post. Inhibitory postsynaptic potential. Right. Okay. I was making sure I didn't spell it wrong. Okay. So what ions produce an EPSP?
Na+.
Right. Sodium. What ions can produce an IPSP?
Chlorine.
Chlorine and potassium.
Chlorine and potassium. Right. Good. Local anesthetics like lidocaine block Volch-Fenwick calcium channels. Why would this make them effective as local anesthetics? Ooh, that's a good question. Glad I thought of it. Blocking Volch-Fenwick sodium channels. Why would that be a? I'm going to stop sharing now because I want to see everybody and start bothering people. Okay, who haven't I heard from today? Carrie Murphy. Hey, Carrie, how you doing? Carrie Murphy.
Yeah.
So, what was the question? Track of it. Oh, what was the question? Hang on a second.
I don't think you had a question.
like the
Oh,
lidocaine
I've got
can
a lot of
do
questions.
something.
Okay, so lidocaine blocks voltage-spinach sodium channels. Why do you think that would be good for a local anesthetic? Murphy left the building. That's okay. Did she leave?
No, I'm still here. I'm just thinking.
You moved around on my screen. Okay, let's bother someone else. Farouk. You unfortunately caught my eye. Farouk Nusulbay. No answer. Farouk. Abu Sabor. Why would blocking sodium channels be a local anesthetic effect? Abu Sabor Tijani. You got it, Abu Sabor. Abdu Sabor, sorry. I keep pronouncing it wrong. No answer? You unmuted yourself, but you're not saying anything. I can't really hear you. Yeah, I can't hear you. How about Celine Ramos? Why don't you tell us what you're talking about there? Celine?
So, oh, sorry. So the channels, since they're blocked, the sodium won't come into the cell, so therefore the cell can't be depolarized, so therefore an action potential can't occur. So all that downstream is blocked.
Yep, exactly. So your sensory neurons are sending action potentials back to your brain. If you block those action potentials, then no transmission can happen. Next question. Why are action potentials all or nothing? That's a good question. Trick question, they're not. No, I'm just kidding, they are. Why are action potentials all or nothing? Strider, that's a name. Wasn't that Aragorn's name before anyone knew who he was? Strider?
Yeah.
Strider. Why? What do you think? Why are action potentials all or nothing? This isn't an easy question. This one's kind of hard.
They're all the same size, so it either takes like the full action potential to reach it to be fired.
Right. You sort of. You're on the right. You're on the right track there. But what makes the action potential go up all the way up? Which ions?
I'm not sure.
So this is kind of a hard question, I guess. So basically, it's all or nothing because if the membrane depolarizes enough to open enough sodium channels, then all the sodium channels open. Okay, because they're all open by depolarization. And if some channels open, that opens other channels, and that opens other channels, and it gets this positive feedback loop going until they all open. So that's why it's all or nothing. If the threshold is not reached during depolarization, it won't repolarize. It won't depolarize, it will repolarize. Correct. Right, so Abdu Sabor, you need to reach the threshold before an action potential occurs. That's true. And then after that threshold gets crossed, all the voltage-dependent calcium or sodium channels open, and that's why it's all or nothing. Because you go past that threshold, boom, it's all. If you go less than that threshold, then it's nothing. It comes back down. And that's, I guess you answered the second part of the question there. You need to reach threshold, otherwise it comes back. Okay, good. Bum, ba, bum, bum, ba, bum, ba, bum. Last question of chapter 2. Oh, this one gets people too. Nobody gets this right, and I think it's easy. The drug Valium, diazepam, increases chloride currents in neurons. What effect will this have on the frequency of action potentials in a neuron?
Wouldn't it be inhibitory because negative is going inside the cell?
Sure. Well done, Yusuf. So many people miss that. They say, well, it must be opening chloride channels, and then the whole brain's I don't know. It just gets weird at that point. Yeah, so diazepam's opening those chloride channels, which is increasing the IPSPs and inhibiting action potentials. Okay, good. Damn. I got to make my exam harder. You guys know too much. Yusuf's definitely getting a different exam than everyone else. He already knows what he's talking about. That's the nice thing about having exams on Moodle. I can give everyone a different exam and make it harder for some people than other people. And that just makes it fun for me. Okay. Describe how presynaptic axon bulb releases neurotransmitters. All right, I don't want to go into that here because it should be easy and it'd take a while to explain. So let's skip over that and get a better one. Here's a good one. Okay, so someone was asking me, I think it was Winter, how do you have to memorize the drug actions? Here's an example of how a drug action would be asked. The venom from a marine snail is very toxic to vertebrates. In the lab, it has been shown to stop the release of neurotransmitters from all presynaptic bulbs, although it has no effect on the action potential in the axon. How do you think it might work? There are many possible answers. Okay, so we've got this unknown drug that blocks release of neurotransmitter from the axon bulb of all neurons. Oh, you can't see the questions? You want to see that question? I'll show the question for you. Okay. Okay. Venom from a marine snail is very toxic to vertebrates. In the lab, is shown to stop the release of neurotransmitter from all presynaptic bulbs, although it has no effect on the action potential. Okay, don't all answer at once. I can't hear you when you're all talking at the same time. Is it one of those chemicals that looks like a neurotransmitter but isn't actually one? Could be, but that would only affect that one particular neurotransmitter. It wouldn't affect all neurotransmitters. So we're talking about something general to all axon bulbs. So like that uptake pump is very specific for that neurotransmitter. So it wouldn't be that. It would have to be something that applies to everything. Let's just look at my answer because I don't know the answer either. Okay. Autoreceptors. Again, autoreceptors are kind of specific for one particular synapse. There are several possible mechanisms by which this would work. The toxin, the one I'm talking about, omega conotoxin, actually blocks the voltage-dependent calcium channels in the axon bulb. And these channels are the same in all neurotransmitter axon bulbs. This blocks transmission because the entry of calcium into the bulb is important for neurotransmitter release. The toxin could theoretically block the internal response to calcium. You could do this by blocking the binding of calcium to proteins on the vesicle that respond to it, or by disrupting the proteins involved in fusing the vesicles to the plasma membrane, the way botulinum toxin does. It could block the forward movement of vesicles. These are 4 general mechanisms that would all apply to all axons. Okay. That's a hard question. I would never ask a question that hard on the test. Believe me. Can you explain what the G protein is? So the G protein is involved in metabotropic receptors, and it's between the receptor and the ion channel. So it's just an intermediary protein. It's either between the receptor and an ion channel, or the receptor and the enzyme that produces cyclic AMP. It's an intermediary there. Okay? Okay. Anyone ever hear of Kinderhook, New York? That's where OK comes from. Here's an interesting historical fact. There was a president in the early 19th century, can't remember his name now, but he was from Kinderhook, New York. And every time he signed a bill into law, he'd sign his name, then go, okay, for old Kinderhook. And it caught on as a saying. Okay, it's true. It's true. Look that up.
That's so random.
It is random. Most of my brain is random. What are 3 different ways that a G protein coupled receptor could interact with an ion channel? Which pathway is the fastest? Which is the slowest? So this is what I was just talking about with the G protein question. And I did answer this earlier today in this class.
So the ion channel one would be the fastest?
Well,
Ion channel?
of metabotrope, this is just metabotropic receptors, which involve a G protein. What is the fastest a route of a G protein activated channel? I kind of answered it there. This is kind of a weird question, but basically in your metabotropic receptors, the G protein could directly open a channel, and that's the fastest, or it could activate cyclic AMP. Cyclic AMP could open the channel, that's the middle, or it could activate cyclic AMP. Cyclic AMP activate the kinase activate the channel. So the longer the pathway, the slower it is. Not a real good question, I guess. Maybe it is, I don't know. Who am I to judge? What would be the effect of an axon bulb on the axon bulb of a drug that formed a calcium pore in the membrane? Oh boy, allowing calcium to pass in freely. What would happen in an axon bulb if you had a drug that allowed calcium to come into it? What does calcium do in the axon bulb? Nobody knows. I'm going to have to start bothering people. No one wants to answer. Who's been lurking? Who's a lurker here? Natasha's a lurker of the nth degree. Natasha, you've got a
Can you repeat the question, please?
You've got a drug that allows calcium into the axon bulb. What does it do? What happens when that happens?
When calcium enters the axon bulb, it would allow neurotransmitters to the vesicles to fuse with the membrane, and neurotransmitters would be released in the synapse.
Okay, good. So let's think about it in a bigger sense, though. Like, you know, one action potential will cause a series of vesicles to release. What happens if you have just calcium flooding in? What happens to that in that axon?
Hyperpolarization? Hyperpolarization?
No, it would be depolarization, just like sodium. What would happen to the neurotransmitter? Maybe I'm beating a dead horse here. Basically, normally an action potential will release that first layer of vesicles. And if you just allowed calcium to fill that bulb, all the vesicles would come forward and they would all release. So basically, that whole axon bulb would just dump all of its neurotransmitter out. Okay, does that make sense?
Yep.
That was Natasha saying yes, just so I would leave her alone. Okay. That's okay. I can deal with that. Oh, someone asked this question earlier, sort of, in a different sense. A person who smokes for the first time tends to experience much more severe effects from a cigarette than someone who smokes frequently. Also, someone who smokes frequently experiences withdrawal symptoms that make it difficult to quit. Given that smoke contains nicotine, provide a reasonable explanation for both of these effects. Reasonable. Reasonable. Reasonable if people could disagree. Who am I going to bother? Ooh, here's someone I don't know and I haven't bothered yet. Kaya Lofton? Kaya? Hello, Kaya.
Yeah.
There she is. So why do you think a first-time smoker would feel the effects of a cigarette much more than a chronic smoker?
Well, their body is not used to that, and they haven't had it before.
Wait. Not their body. Let's go to the cellular level. What's happening at the cells? Don't use the term get used to.
What'd you say?
Don't use the term get used to. Tell me what's happening in the cells of the first-time smoker versus the long-time smoker.
I'm not too sure.
Okay.
A person who smokes more would have less receptors for it, so it wouldn't like kill them as much as those who have more receptors for it, so they feel more of an effect immediately.
Right, exactly. So someone who's chronically smoking is downregulated their receptors, so they don't feel it as much, versus someone who has just taken it for the first time. All their receptors are normal, and they get really slammed by it. Okay. On the other hand, why is it someone who is a chronic smoker goes into withdrawal when they don't smoke?
Wait, can you repeat that question again?
Okay, but let me ask someone else to answer it because you've done well for yourself today. Krista Novello. Krista. Are you here, Krista? Hello, Krista. Can we see your face? We don't have to. That's all right. Oh, there she is. Okay, so why is it someone who smokes chronically goes into withdrawal when they don't have a cigarette? Again, receptors. Are you talking? You're muted. You're muted. I can't hear you. Okay.
Is it because like a few receptors like become available and then they're able to respond, or
Can you say that again? We're talking about a chronic smoker who doesn't have a cigarette one day. What happens when you smoke chronically to your receptors?
they become blocked, right?
Downregulated. You've got fewer of them. Okay, so what happens if you don't take a cigarette now? Shall I let you off the hook?
Please.
Okay. Addie Strong, do you have an answer here?
No, I don't.
Okay. Hang on one second. Ah. Yeah, I got it. Sorry about that. Okay, so if you're a person who smokes all the time, then you've downregulated your receptors. And now to get enough stimulation to feel normal, you have to keep smoking. Because when you stop smoking, you don't have the nicotine anymore. And the normal amount of acetylcholine in your brain is not enough to stimulate those few receptors that are left. So unless you keep taking that drug, you're going to go into withdrawal. So bottom line of this being, first time you take it, your receptors are high and boom, it hits you really hard. After a while, your receptors go down and you have to keep taking it or else you're going to go into withdrawal from it. Okay, 4:29. I didn't think we'd last this long, but this is pretty good. Let's open the floor again to questions one more time before we call it a day.
What does the endogenous neurotransmitter mean again?
Endogenous. Good question. So endogenous means that's what's in your body already, what's already being used by your body. Exogenous would be a drug that you take.
So and endogenous ones are just like naturally produced.
Right, exactly. Gen means produced, endo means inside, produced inside your body, endogenous. Okay, any other questions? Okay, no more questions? I have one. Sean Reeser always has a question. You're a good man, Sean.
Where's the bonus points at?
Is this Zoom meeting going to be uploaded before the exam? Yeah, I'll process it. I'll try and get it up today. Well, I will get up today. I'm just not sure when. Maybe later tonight. See, it has to download and then process in YouTube, and that whole thing takes a good half hour, but I'll get it up there as soon as I can. Will there be any opportunities for makeup/extra credit for exams? Next question. Oh, Alexis, thank you. Oh, you're welcome, Alexis. I'm ignoring Sean's question. That's not a good question. They say there are no dumb questions. They're not right. Let's see. So bonus points in this class are mainly on the board, on the question board. If you ask a good question, answer a good question, then you get bonus points that way. Yeah, Sean's not going to need the extra credit. He's a playa. My GPA disagrees. Okay, guys. Any other questions, or should we call it a day?
Let's call it a day.
Well done, Winter. We're going to call it a day. And Thursday, meet back here at our normal class time, and that's when the exam will be. And I'm going to put you all up on the board, and I'll be here in case you need to ask me questions. You can chat me privately, or we can talk to the class that way.
Thursday?
Wednesday, sorry.
You scared me for a second.
I always get confused. Okay, guys.
Wait, so we need to be on the Zoom call for the test?
I guess you don't have to be on it. You can do it without Zooming. It's just that I'll be here so that if you need to ask me questions, I'll be here.
Okay.
You'll be answering questions?
Yes, not answering the questions from the exam, but answering questions about the exam. See, you thought you were going to get me there. Okay, everybody happy? All right, we'll see you Thursday.
Bye-bye. Thank you.